Right now, there is a confirmed planet with 4 suns in its sky, 2 blazing close together on one side, 2 more burning as brilliant distant points on the other. Subscribe if you want more of the cosmos. This is white space. Settle in. The Milky Way contains somewhere between 200 and 400 billion stars. Most astronomers now agree that almost every single one of them hosts at least one planet. That alone, taken in its full arithmetic weight, means we are looking at a number of worlds so vast that human intuition simply refuses to hold it. But beyond the count, beyond the sheer scale, the real discovery of the past 3 decades is how strange those worlds can be. The universe does not default to simplicity. It generates configurations that violate every expectation our solar-centric perspective has trained us to hold. Among those configurations, one stands out with particular force: a planet confirmed to orbit not 1 star, not 2, but in a system where 4 stars govern its sky simultaneously. The system is designated Kepler-64. It lies in the constellation Cygnus, roughly 5,000 light-years from Earth. At its heart, 2 stars, one slightly more massive than the Sun, one slightly less, orbit each other in a tight gravitational pairing, completing 1 revolution every 20 days. Their separation is modest, less than a fifth of the distance between the Sun and Mercury. At this range, they function almost as a single composite object, their combined gravity dominating the inner system. Around this binary pair, at a distance of about half an astronomical unit, a planet traces a stable orbit every 138 days. Astronomers call it PH1b, the PH denoting Planet Hunters, the citizen science project through which it was found, and that discovery is itself remarkable. The Kepler Space Telescope was designed to search for planets by monitoring the brightness of stars. When a planet passes in front of its star, it blocks a tiny fraction of the light, producing a characteristic dip in the recorded brightness. In a binary system, the 2 stars also eclipse each other periodically, generating their own brightness variations. Sorting the transit signal of an orbiting planet from the rhythmic eclipses of 2 orbiting stars is not trivial, and the automated detection pipelines used by the Kepler mission missed PH1b. What caught it was human pattern recognition, volunteers sifting through raw light curves on the Planet Hunters website, trained to notice anomalies. In 2012, those volunteers flagged the transit signature that professional follow-up observations confirmed as a genuine planet in a circumbinary orbit. But Kepler-64 does not stop at 2 stars and 1 planet. Far out in the system, at a distance of roughly 1,000 astronomical units from the central binary, a second pair of stars orbits the whole inner arrangement. This outer binary is itself gravitationally bound to the system. The result is a hierarchical quadruple, 2 pairs of stars, one nested inside the other, with a planet orbiting the inner pair. PH1b is approximately 6 times the radius of Earth. This places it in the population of worlds astronomers call mini-Neptunes or sub-Saturns, planets likely composed of a rocky or icy core surrounded by a substantial envelope of gas. Its density and size do not suggest a solid, walkable surface. But consider the sky such a world would present. The inner binary, 2 stars separated by a tiny fraction of the distances we are accustomed to between stellar objects, would appear as 2 distinct suns on the same side of the sky, visually close enough that their light blends at sunrise and sunset, producing color gradients and shadow geometries that nothing on Earth ever casts. The outer binary, far more distant, would appear as 2 exceptionally bright stars, brighter than anything in our own night sky, following a slow progression across the celestial sphere over years as they orbit the system. Seasons on such a planet would bear no resemblance to anything in our experience. The planet's orbit around the central binary introduces 1 periodic cycle. The varying distance and angle of the outer binary introduces a second, much slower modulation. The combination of both produces a pattern of illumination and radiation exposure that repeats on timescales nested within each other. Short cycles inside long cycles, with no simple dominant period. Planet formation theory has traditionally assumed a single gravitating center. The existence of PH1b and other confirmed circumbinary planets found by Kepler, such as Kepler 34b, Kepler 35b, and Kepler 47's multiplanet system, forces that theory to accommodate a much wider range of starting conditions. A protoplanetary disk forming around two closely orbiting stars is subjected to gravitational torques that tend to disrupt it, truncating its inner edge and creating turbulence that should, in principle, impede the accumulation of solid material into planetesimals. And yet the planets are there. Something in the physics of disk evolution and particle accumulation navigates these obstacles and produces coherent worlds. How many more planets like PH1b are waiting to be found in systems like this one? Systems where the stellar complexity has placed the transit signatures just beyond the reach of automated detection is a question that future missions with more sensitive instrumentation and more thorough data analysis will begin to answer. For now, Kepler 64 stands as proof that the universe builds planets wherever it can, indifferent to the difficulty of the problem. Moving inward through our own solar system, from the remote catalogs of confirmed exoplanets to the planets we have been studying for centuries, the second largest world in the Sun's family offers a set of puzzles that are, in some respects, even harder to resolve than those posed by distant circumbinary systems. We can observe PH1b only as a transit signal and a set of orbital parameters. Saturn we have watched for years with spacecraft, and it still withholds most of its secrets. Saturn is, to the eye and to the photographic plate, the most immediately beautiful object in the solar system. Its ring system extends 280,000 kilometers from the planet's center, farther than the distance between Earth and the Moon, yet is typically less than a kilometer thick. The rings are composed of ice particles ranging from dust grains to boulders several meters across, and they reflect sunlight with extraordinary efficiency. Saturn's atmosphere, visible through even a modest amateur telescope, shows bands of pale cream, tan, and soft gold, cut across by the thin dark line of the ring shadow and occasionally disrupted by white storm systems that swell to continent-sized proportions. The most dramatic of these storms erupt from the planet's northern hemisphere in a pattern that repeats approximately every 28 to 30 Earth years, each time Saturn's northern hemisphere approaches summer solstice. The 2010-2011 Great White Spot was the most closely monitored of these events in the spacecraft era. Within weeks of its first appearance, it had grown into a storm system that encircled the entire planet, its turbulent head generating lightning at a rate estimated at 10 strikes per second, its wake disrupting the atmospheric band structure for months. The Cassini spacecraft, in orbit at the time, observed it continuously from above. Earth-based amateur astronomers photographed it every clear night. The storm eventually consumed itself, the disturbances it had created interfering with the convective engine that had powered it, and the northern hemisphere gradually returned to its banded structure. The energy released by a single one of these storms over its duration exceeds the total annual energy consumption of human civilization by several orders of magnitude. The winds responsible for those storms are measured in the hundreds of meters per second. Near Saturn's equator, jet streams blow at speeds exceeding 1,600 kilometers per hour, faster than any wind ever recorded on Earth, faster than the speed of sound at sea level. These winds are not powered by the sun. Saturn receives only about 1% of the solar energy per unit area that Earth receives, and the gradient between equatorial and polar heating is too small to drive jets of this magnitude. The real engine is internal. Saturn radiates roughly 1.7 times as much energy as it receives from the Sun. That excess heat rising from the deep interior drives the atmospheric circulation. The bands and zones visible in the cloud deck are the surface expression of convective columns extending deep into the planet. At the cloud tops, composed mainly of ammonia crystals at temperatures around minus 178 degrees Celsius, the atmosphere is already alien by any Earth standard. Below the ammonia layer, at deeper and warmer levels, ammonium hydrosulfide clouds form, darker and more opaque. Deeper still, where temperatures rise above the freezing point of water. Water ice and water droplet clouds are expected to exist, though no probe has yet penetrated to these depths in Saturn's atmosphere. The Galileo probe, which descended into Jupiter in 1995, entered what turned out to be an unusually dry region, sampling less than 1% of the planet's volume before being crushed. Saturn has never had a dedicated atmospheric entry probe. What we know of Saturn's interior comes primarily from three sources: measurements of its gravitational field by Cassini ring seismology, the use of patterns in Saturn's rings as a readout of internal oscillations, and theoretical models constrained by both. The gravitational field measurements, gathered during Cassini's grand finale, orbits in 2017 when the spacecraft flew between the rings and the planet for the first time, revealed that Saturn's interior is not well mixed. The heavy elements, the rock and ice that formed the original core, are distributed in a gradual concentration gradient rather than segregated into a sharp central core. Material that was once a distinct rocky core has dissolved, diffused, or been stirred outward into a fuzzy extended region that transitions imperceptibly into the metallic hydrogen above it. The metallic hydrogen itself begins at roughly 30,000 kilometers below the cloud tops, where the pressure exceeds 3 million Earth atmospheres. At this pressure, hydrogen, the most abundant element in the universe, undergoes a phase transition into a state without an analog in ordinary chemistry. The electrons that normally bind to hydrogen atoms become free, able to move through the material the way electrons move through a conductor. The result is a substance that is simultaneously dense, hot, opaque, and electrically conductive. This metallic hydrogen layer is the seat of Saturn's magnetic field, generated by the same dynamo process that operates inside Earth's liquid iron core. Electrical currents circulating in a conducting fluid, organized by rotation into a coherent global field. Saturn's magnetic field has one feature that puzzles planetary scientists intensely. It is nearly perfectly aligned with the planet's rotation axis. Earth's magnetic field is tilted by about 11 degrees from its rotation axis, Jupiter's by about 10 degrees. Most planets with internally generated magnetic fields show some misalignment, because misalignment is in fact necessary for the dynamo mechanism to sustain itself. A perfectly aligned, perfectly symmetric system would not generate a sustained field at all. Saturn's alignment is less than 1 degree. How the dynamo manages to sustain itself under these conditions remains an unsolved problem. One proposed explanation involves a thin layer, deeper in the atmosphere than the metallic hydrogen, but above the transition zone, where helium or other heavy elements may be stably stratified, a calm layered zone that filters the magnetic fluctuations generated below into a smooth, axially symmetric field by the time they reach the surface. This theory is elegant, but confirming it would require measurements inside Saturn that no existing or planned spacecraft can make. At the deepest levels, in what we loosely call the core, temperatures may exceed 12,000 degrees Celsius, hotter than the surface of the Sun. Pressures reach tens of millions of Earth atmospheres. Under these conditions, the behavior of matter departs so far from anything studied in terrestrial laboratories that even our best equations carry substantial uncertainty. The elements that formed Saturn's original core, silicon, iron, magnesium, oxygen, would be in states that exist nowhere else in the solar system. They interact with the surrounding metallic hydrogen in ways that depend on solubility at extreme pressures, a property we are only beginning to measure experimentally using diamond anvil cells capable of generating a few million atmospheres in a laboratory setting. To reach the conditions inside Saturn's center, we would need to increase that pressure by more than an order of magnitude beyond what any current apparatus achieves. Saturn continues to surprise us. Every time we refine our models, the planet reveals another layer of complexity. After 13 years and 294 orbits, the Cassini mission ended in September 2017, and its final data, still being analyzed, continue to produce discoveries. Closer to home, the Moon, our nearest companion in space, is a world of quiet extremes. No atmosphere to carry sound, no liquid water to erode the landscape, no plate tectonics to resurface and renew. What the Moon records it keeps impact events from 4 billion years ago are preserved on its surface as crisply as the day they occurred, because nothing has come along to erase them. This makes the Moon an archive, a record of the early solar system locked in stone. A tour of that archive begins with the formation regions. The vast, dark plains visible to the naked eye are not lowlands filled with water, as early astronomers once imagined, but ancient lava flows. Between 3 and 4 billion years ago, volcanic eruptions flooded the Moon's large impact basins with basaltic lava that cooled into the dark, relatively smooth surfaces we now call the lunar Maria. The largest connected expanse of this material, the Oceanus Procellarum on the western near side, covers an area larger than the Mediterranean Sea. Within these volcanic plains, lava tubes are common tunnels formed when the outer surface of a lava flow cools and solidifies while molten rock continues to drain through the interior. When the eruption ends, the drained tunnel remains covered by its hardened roof. Some of these tubes on the Moon are enormous. The Marius Hills complex contains a pit roughly 50 meters across and 50 meters deep where the roof of a tube has collapsed, offering a window into a cavity that may extend for kilometers. Proposals have been made to site future lunar habitats inside lava tubes, where the thick rock overhead would provide shielding from cosmic radiation and micrometeorite impacts. The crater Tycho in the Moon's southern highlands is one of the most visually striking features on the entire surface. At 86 kilometers in diameter and roughly 100 million years old, it is young enough by lunar standards to retain crisp, sharp rim walls and a central peak that rises more than 2 kilometers above the crater floor. The rays of ejected material surrounding Tycho extend across the entire near side, bright streaks of freshly excavated rock visible from Earth with the unaided eye. The impactor that created Tycho was probably a few kilometers across, and its collision released energy equivalent to billions of nuclear weapons detonating simultaneously. In contrast to Tycho's youthful sharpness, the highlands themselves are ancient terrain that dates back to the first few 100 million years of lunar history, saturated with craters from the period of heavy bombardment that affected the entire inner solar system. These highlands are composed of anorthosite, a light-colored rock rich in the mineral plagioclase feldspar, crystallized from the lunar magma ocean that covered the entire Moon in its earliest phase, when it was still mostly molten. The Moon cooled from the outside in. Lighter minerals floated to the surface. Heavier minerals sank, producing a differentiated structure that future sample return missions are designed to probe more deeply. The Moon's south pole holds what may be its most scientifically valuable real estate: permanently shadowed craters where temperatures never rise above minus 150 degrees Celsius, and ancient ice deposits are believed to have accumulated over billions of years. Neutron spectrometer data from the Lunar Prospector mission in the late 1990s first suggested elevated hydrogen concentrations in these regions. The L-CROSS mission in 2009 confirmed water ice directly. A 2,400 kilogram spacecraft impactor deliberately slammed into the floor of the KBOS crater, and spectrometers on the trailing observation spacecraft detected water in the debris plume. The water almost certainly arrived as comets and water-bearing asteroids struck the young moon, with some of the ejected vapor eventually migrating to the polar cold traps and freezing out there. That ice, if it can be mined and processed, represents both water for drinking and oxygen for breathing, and hydrogen and oxygen for rocket propellant. It makes the lunar South Pole not just a scientific target but a strategic one. Among the moon's most geometrically striking surface features are the wrinkle ridges, long sinuous landforms that run for hundreds of kilometers across the volcanic maria, formed as the basaltic plains cooled and contracted, compressing the surface into gentle but distinct folds. Dorsum Circle, stretching 190 kilometers across Mare Imbrium, is one of the more prominent examples. A long, low spine of compressed lava that catches the light at shallow sun angles and casts a shadow revealing its true relief. To traverse such a ridge on foot would be barely noticeable. The slopes are gentle. The height rarely exceeds a few hundred meters, but seen from orbit at the right illumination, it stands out like a seam. The moon's highland craters tell a different story from the impact scars of the volcanic plains. In the southern highlands, the Schrödinger Basin, 306 kilometers in diameter, one of the best preserved large impact basins on the moon, contains a partial inner ring structure, volcanic vents along its floor, and a record of multiple geologic events layered one on top of another. It is a destination that lunar geologists have argued for decades deserves a dedicated surface mission, because it sits at the interface between the ancient southern terrain and the geological events associated with the South Pole Aitken Basin. Itself a colossal structure 2,500 kilometers across and 8 kilometers deep, the largest confirmed impact crater in the solar system. The South Pole Aitken Basin excavated so deeply into the lunar crust that it may have exposed material from the mantle, rock that has never been seen on the surface, and that would answer fundamental questions about the moon's internal composition and thermal history. Samples from its floor would be unlike anything returned by Apollo, which landed exclusively in the equatorial and mid-latitude regions of the near side. The difference in composition between the lunar near side, where volcanic activity was concentrated, and the far side, where the crust is thicker and volcanism was rarer, remains one of the largest unresolved puzzles in lunar science. The answer is buried in the geology of terrains we have so far only photographed from orbit. The Artemis program, the missions of China's CLPS commercial lunar payload service, and the proposed International Lunar Gateway Station all converge on the same fundamental recognition. The moon is not a destination we have finished with, we have barely begun. On August 13, 1898, a German amateur astronomer named Gustav Witt was examining a set of photographic plates exposed during a routine survey when he noticed a moving object, a point of light that had shifted its position between exposures in a way that only a body within the solar system could do. He had discovered an asteroid. It was given the number 433 and the name Eros, after the Greek deity of love. And for the next century, it would orbit the Sun largely unvisited, crossing Earth's orbital path at perihelion. Occasionally bright enough to be tracked without specialized equipment, but visited only by telescopes. Eros is a member of the Amor group, near-Earth asteroids that cross Mars's orbit and approach Earth's but do not cross it. Its orbit carries it between 1.3 and 1.78 astronomical units from the Sun, completing one revolution every 1.76 years. It is not spherical. Eros is elongated, 34 kilometers long, 11 kilometers wide, twisted slightly along its long axis, its shape resembling a peanut or a worn-down shoe. This irregular shape, with its asymmetric mass distribution, causes Eros to rotate in a tumbling motion rather than the clean spin of a more symmetric body, completing one rotation every 5.27 hours. NASA's Near Shoemaker spacecraft, the Near-Earth Asteroid Rendezvous mission, was launched in February 1996 with the explicit goal of studying Eros in detail. It was the first spacecraft ever sent specifically to orbit an asteroid. The journey was not straightforward. In December 1998, as the spacecraft approached Eros for its planned orbital insertion burn, a software error caused the main engine to shut down prematurely. Contact was lost for 27 hours. When communication was re-established, the opportunity for the originally planned orbit insertion had passed. Near Shoemaker flew past Eros from a distance of about 3,800 kilometers, capturing several hundred images before continuing on an unplanned additional loop around the Sun. A year later, in February 2000, the spacecraft successfully entered orbit around Eros. The initial orbit was 323 kilometers from the asteroid's center. Over the following months, the altitude was progressively reduced to 200 kilometers, then 100, then 50, then 35. At 35 kilometers, the spacecraft was close enough to capture images showing features just a few meters across. What those images revealed was a surface of remarkable variety and, in places, remarkable strangeness. Eros is covered with more than 100,000 craters larger than 15 meters in diameter, a testament to 4.5 billion years of impacts in the asteroid belt. Yet mixed among these craters is something unexpected, a scarcity of small craters relative to what impact models predict. When a large impactor strikes Eros, the resulting seismic vibration shakes the entire small body. On a large planet with its deep gravity well, ejecta from an impact eventually settles back in a localized area. On Eros, with its weak gravity, ejecta can travel around the world and resettle globally, filling in and burying small craters. This process, known as seismic shaking or impact-induced regolith migration, operates differently on small bodies than on large ones, and studying it on Eros gave planetary scientists their first close look at this mechanism in action. Eros is also covered with boulders, roughly 1 million rocks larger than 1 meter, strewn across the surface in densities far higher than initial models predicted. Some boulders are tens of meters across. In the low gravity of Eros, about melt 0.6 times Earth's surface gravity. A person standing on the surface would weigh less than a few grams and could leave the surface with a gentle jump. The escape velocity from Eros is only 10 meters per second, a brisk running pace. This means that during large impacts, a substantial fraction of the ejected material escapes into space entirely, never returning to the surface. On February 12, 2001, with its primary mission complete and fuel running low, ground controllers at the Applied Physics Laboratory in Maryland decided to attempt something that had never been done before and had not been part of the original mission plan: a controlled landing on the asteroid's surface. Near Shoemaker fired its thrusters in a carefully planned sequence of 4 burns, slowing its approach. It descended through an environment where the gravitational acceleration was so weak that the entire descent, from the last orbit to the surface, took about 4.5 hours. The spacecraft survived the landing, touching down at roughly 1.5 meters per second, bouncing at least once, and coming to rest in a shallow depression near the southern hemisphere. It continued to transmit data for 16 days. The final images, captured from altitudes of a few dozen meters, showed the surface with a resolution of a few centimeters, the most detailed views of an asteroid surface recorded up to that point. When the transmission finally ceased, nearshore maker had returned 160,000 images and gathered data that would take years to fully analyze. Among the findings, Eros is a primitive object compositionally similar to chondritic meteorites, not significantly altered by the heat processing that differentiated larger bodies like Earth or the Moon. It preserves material from the early solar system in nearly its original chemical state. The mission remains, decades later, one of the most elegant in the history of planetary exploration. A spacecraft launched to study a world from orbit, staying far longer than planned, and finally walking itself gently down to the surface as its last act. The fourth planet from the Sun has been the subject of more missions, more speculation, and more sustained scientific attention than any other body in the solar system except Earth itself. Mars has earned this attention because no other world outside Earth shows such clear evidence of a geological and climatic past so different from its present. The Mars we observe today, cold, dry, with an atmosphere 1% as thick as Earth's, swept by dust storms that can shroud the entire planet for months, is not the Mars of 4 billion years ago. And the story of how it became what it is tells us something essential about what makes planets habitable and what takes habitability away. The most immediate indication of Mars's different past is the dichotomy between its two hemispheres. The southern highlands, heavily cratered, ancient, sitting several kilometers above the Martian datum, preserve a record of heavy bombardment from the solar system's early history. The northern lowlands are smoother, younger, sitting lower. This asymmetry has no complete explanation. The leading hypothesis involves a single massive impact early in Mars's history, so large it excavated a shallow basin covering nearly a third of the planet's surface. If correct, this would make the northern lowlands a single impact structure, the largest in the solar system, a conclusion that is difficult to verify because the original surface has been substantially reworked by volcanic activity and erosion. The volcanic record on Mars is dominated by a single feature, the Tharsis Bulge, a region of elevated terrain, roughly the size of North America, that formed as a consequence of sustained volcanic activity over billions of years. At its margins, the plumbing of this system produced the Tharsis Montes, three massive shield volcanoes lined up in a row, and at its northwestern edge, Olympus Mons, the tallest volcano in the solar system. Olympus Mons rises approximately 20 kilometers above the surrounding plains. Its base spans 600 kilometers. Its caldera complex at the summit is 80 kilometers across and several kilometers deep. The volcano is so large that standing on its outer slopes you would not see the summit. It lies beyond the horizon, even at an elevation of 22 kilometers. The weight of the Tharsis Bulge deformed the crust of Mars globally. Stretching and fracturing on the opposite side of the planet produced Valles Marineris, a canyon system that extends 4,000 kilometers, reaches depths of 7 kilometers, and would span the entire continental United States. Valles Marineris is not, despite its name, a river valley. It is a rift structure, a place where the crust pulled apart under the stress of Tharsis' formation. Some sections contain layered deposits that record a history of sediment accumulation in ancient lakes or wet periods. Others show evidence of massive landslides, some of the largest ever identified in the solar system, triggered by the steep canyon walls collapsing over millions of years. The water that shaped ancient Mars left its traces everywhere. The Mars Reconnaissance Orbiter, the ESA Mars Express, and a succession of rovers and landers have collectively mapped river delta deposits, ancient lake beds, shoreline terraces, and thousands of channels carved by flowing water. Curiosity's landing site in Gale Crater was chosen precisely because the crater once held a lake, a body of standing water, that persisted for perhaps tens of thousands to millions of years, depositing fine sediment that compacted into the mudstones the rover has been drilling into since 2012. Those mudstones contain organic carbon, not proof of ancient life, but confirmation that the chemical ingredients for life were present in a liquid water environment for an extended period. Where did the water go? The answer involves two mechanisms working in parallel over billions of years. The first is escape to space. Mars's weak gravity, about 38% of Earth's, is less effective at retaining an atmosphere. Solar wind particles, the constant stream of charged particles emitted by the sun, gradually eroded Mars's upper atmosphere over time. Earth is protected from this erosion by its global magnetic field, which deflects the solar wind before it reaches the atmosphere. Mars lost its global magnetic field roughly 4 billion years ago, when its interior cooled enough that the convective dynamo in its core ceased. Without that shield, atmospheric erosion accelerated, and as the atmosphere thinned, surface water became unstable and eventually disappeared. The second mechanism is incorporation into the subsurface. Mars's polar ice caps contain water ice mixed with frozen carbon dioxide. Subsurface ice has been detected by ground-penetrating radar at mid-latitudes. Buried glaciers, recognized by their characteristic surface expressions of ridges and flow features, cover substantial areas of the mid-latitude terrain. Some of this ice was deposited during past periods when Mars's axial tilt was different from its current 25 degrees. Periods when the poles received more direct sunlight and polar ice migrated to the mid-latitudes in what planetary scientists call ice ages in reverse. A 2022 study published using data from the Shared radar sounder on the Mars Reconnaissance Orbiter estimated that the total water ice stored in the mid-latitude belts of Mars, if melted, would cover the planet in a global layer approximately 1.5 meters deep. Mars does not give up its water record without a fight. Dark streaks appearing on certain steep slopes, first identified in 2011 and called recurring slope lineae, raise the possibility of liquid water flowing on the present-day surface. Subsequent analysis complicated this picture significantly. The streaks appear in season, flow downhill and then fade, but chemical analysis from orbit suggests they may be dark dust flows rather than liquid water. The search for present-day liquid water has shifted underground. A radar detection reported in 2018 identified a reflective layer roughly 20 kilometers below the surface near the southern pole, interpreted as a subglacial lake of liquid water, kept liquid by the pressure of overlying ice and by residual geothermal heat. This interpretation has been challenged. The reflective layer might alternatively be caused by specific clay minerals or other materials, but the debate itself shows how seriously the question is taken. The chemistry of Mars's soil presents its own puzzles. The Phoenix lander, which touched down in Mars's northern Arctic plains in 2008, discovered perchlorate compounds in the soil, oxidizing salts formed by ultraviolet radiation acting on the surface over billions of years. On Earth, certain bacteria metabolize perchlorates for energy, and some researchers have proposed that if microbial life ever existed on Mars, it might have adapted to use this abundant chemical as a metabolic resource. But perchlorates are also toxic to many organisms, and their widespread presence in the soil complicates the interpretation of organic chemistry results. The Viking landers in the 1970s detected no unambiguous organic molecules in Martian soil, a result that puzzled scientists for decades. In 2018, Curiosity's sample analysis at Mars Instrument identified complex organic molecules including chlorobenzene and dichloroethane in 3 billion-year-old mudstone at Gale Crater. These organics were not definitively biological. They could have been delivered by meteorites, but they demonstrated that organic chemistry can be preserved in Martian rock on billion-year timescales, which changes the calculation for what future missions might find. The atmosphere of Mars, thin as it is not static. It participates actively in the planet's ongoing geology. Each Martian year, somewhere between 25 and 40% of the atmospheric carbon dioxide freezes out at the poles during winter, depositing a layer of dry ice several meters thick. In summer, that ice sublimes directly back into the gas phase, reversing the cycle. This seasonal exchange of carbon dioxide between atmosphere and surface generates pressure waves that propagate globally, influencing wind patterns and dust transport. Dust storms on Mars can begin as local events, a small region of elevated winds lofting fine dust into the lower atmosphere, and under the right conditions, these regional storms can cascade into global events that blanket the entire planet for months. The 2018 global dust storm was the most severe in years of spacecraft observation. It ended the Opportunity rover's mission by blocking enough sunlight that the solar-powered vehicle could no longer maintain its batteries. Opportunity had been operational for 15 years, traveling more than 45 kilometers from its landing site. The Mars we will send humans to, perhaps in the 2030s or 2040s, will be a world whose ancient story is just being read. Samples returned by the Perseverance rover, currently cached at Jezero Crater, will arrive on Earth in the 2030s under the current Mars sample return plan, and their analysis will constrain the history of that lake system with a precision no remote measurement can match. What they will tell us about whether Mars once hosted life, microbial, simple, brief, remains genuinely unknown. Everything we know about the cosmos beyond our solar system has reached us through light or through phenomena closely related to it. The electromagnetic spectrum is our only messenger from the distant universe. We cannot travel to the Andromeda galaxy to take a sample. We cannot send a probe to a neutron star and wait for it to return. We can only wait for signals to arrive and read them carefully when they do. Light, in the physicist's description, is an electromagnetic wave, oscillating electric and magnetic fields propagating through space at 299,792 kilometers per second. This speed is not merely fast. It is, as far as any experiment has established, the maximum speed at which any physical influence can propagate. Information cannot travel faster than light. Cause and effect are separated by light travel time. When we look at the Sun, we see it as it was 8 minutes ago. When we look at Proxima Centauri, the nearest star beyond our Sun, we see it as it was 4 years ago. When we look at the Andromeda galaxy, we see it as it was 2.5 million years ago before our species existed. This time delay is not an inconvenience, it is the fundamental structure of the universe. It means that the farther we look, the further back in time we see. Telescopes are time machines. The James Webb Space Telescope, positioned 1.5 million kilometers from Earth at the Sun-Earth Lagrange point, has captured light from galaxies whose photons were emitted less than 300 million years after the Big Bang, less than 2% of the universe's current age. Looking at those images is literally seeing the universe's infancy, but light does not travel in straight lines near massive objects. This is one of the central predictions of general relativity, the theory Albert Einstein completed in 1915. Newton's theory of gravity described it as a force, a pull acting instantaneously between masses across any distance. Einstein's version was different at its foundation. Gravity in general relativity is not a force at all. It is the geometry of space-time. Mass curves space-time around itself. Objects moving through that curved space-time follow paths that appear to a distant observer, like the result of gravitational attraction. But locally, each object is simply following the straightest possible path through a curved space. The first experimental confirmation of this prediction came in May 1919 during a total solar eclipse visible from West Africa and Brazil. The British astrophysicist Frank Watson Dyson had organized 2 expeditions, one to Sobral in northern Brazil, led by Andrew Crommelin, one to the island of Principe off the equatorial Guinean coast, led by Arthur Eddington, specifically to photograph stars near the Sun's edge during totality, when the Sun's disk would be blocked by the Moon and faint stars in that part of the sky would become visible. The prediction was specific. Starlight passing close to the Sun should be deflected by 1.75 arcseconds. Newton's theory, if gravity acted on light at all, predicted only half that amount. Eddington's plates from Principe and the Sobral photographs showed deflections consistent with Einstein's value. On November 6, 1919, the result was announced jointly by the Royal Society and the Royal Astronomical Society in London. The next day's London Times headline read, "Revolution in Science. New theory of the universe. Newtonian ideas overthrown." The bending of light by gravity produces a phenomenon now called gravitational lensing. When a massive object, a galaxy, a cluster of galaxies, a compact clump of dark matter, happens to lie between Earth and a more distant light source, the gravitational field of the intervening object bends the light from the background source around it in multiple directions. If the alignment is close to perfect, the background source is smeared into a ring centered on the foreground lens, a structure called an Einstein ring, predicted by Einstein himself in 1936, though he doubted at the time that such an alignment would ever be observed in practice. The first confirmed Einstein ring was detected in 1988 using the Very Large Array Radio Telescope in a system designated MG 1131+0456. Since then, hundreds have been catalogued when the alignment is slightly off-center or when the foreground lens has a non-spherical mass distribution. The ring breaks apart into multiple arc-shaped images or into discrete point sources arranged around the lensing object. One of the most striking examples is H0435-121223, a quasar 10 billion light-years distant whose light is split into 4 bright images arranged almost perfectly symmetrically around a foreground galaxy 3.7 billion light-years away. The geometry produces a cross-like arrangement of the 4 images, a configuration called an Einstein cross. By measuring the brightness and positions of these 4 images and tracking how they vary over time. Because the quasar itself is variable, astronomers can measure the mass of the lensing galaxy, map the distribution of dark matter in its halo, and even derive an independent measurement of the Hubble constant, the rate at which the universe is expanding. Gravitational lensing has become one of the most powerful tools in observational cosmology. The Hubble Space Telescope's deep field images of galaxy clusters reveal dozens of arc-shaped images of background galaxies, each arc a distorted view of a galaxy billions of light years further away. The degree of distortion encodes the total mass along the line of sight, visible matter and dark matter together. Without gravitational lensing, dark matter would remain almost entirely invisible, detectable only through its gravitational influence on the rotation curves of galaxies or the orbital dynamics of galaxy clusters. Lensing gives it a shape, a distribution, a geography, but the deepest consequence of general relativity reached us only recently. Einstein's theory predicts that when massive objects accelerate, they produce ripples in spacetime itself, gravitational waves, disturbances in the fabric of the universe propagating outward from their source at the speed of light. Einstein himself calculated these waves in 1916, but he was skeptical they would ever be detected. The distortions they produce in space, even from cataclysmic events, are almost inconceivably small. On September 14, 2015, the Laser Interferometer Gravitational Wave Observatory, two L-shaped detectors in Louisiana and Washington state, each with arms 4 kilometers long, registered a signal lasting 0.2 seconds. The signal had the characteristic form of a chirp, rising frequency and increasing amplitude, the signature of two massive objects spiraling toward each other and merging. Analysis established that the signal came from two black holes, each roughly 30 times the mass of the Sun, merging 1.3 billion light-years away. The merger released more energy in a fraction of a second than all the stars in the observable universe combined emit in that same interval, and almost all of it left as gravitational waves. The distortion that LIGO detected, averaged across its 4-kilometer arms, was a displacement of 4,000ths of the diameter of a proton. That detection, confirmed by a second gravitational wave event 2 months later, and by dozens of subsequent detections in the years that followed, opened a new window onto the universe, a window that carries information no electromagnetic wave can carry. Gravitational waves pass through matter without being absorbed or scattered. They are not blocked by dust clouds. They are not absorbed by intervening galaxies. They arrive from sources that emit no light at all, the mergers of black holes that cannot by definition be seen. The universe has been speaking in gravitational waves since its beginning. We have only recently learned to listen. In 2017, the LIGO and Virgo detectors jointly recorded a gravitational wave signal from the merger of two neutron stars, the first such detection. Unlike the black hole mergers detected previously, this event also produced light, a brief intense flash of gamma radiation, followed by an optical counterpart that faded over days as the radioactive debris expanded. 69 electromagnetic observatories on Earth and in space turned to the same small region of sky within hours of the alert, watching the afterglow of a neutron star collision in real time. The material ejected by this event, a spray of heavy elements synthesized in the extreme conditions of the merger, included gold, platinum, and uranium. The collision of two neutron stars is where these elements are made. The gold in a ring, the platinum in a catalyst, the iridium in the tip of a fountain pen. These atoms were forged not in the nuclear furnaces of ordinary stars, but in the final moments of two collapsed stellar remnants spiraling together and annihilating. Gravitational wave astronomy delivered this understanding not as a theory, but as a direct observation. The network of gravitational wave detectors continues to grow. Kagra in Japan joined the network in 2020. A European facility, the Einstein telescope, still in the planning stages, would be 10 times more sensitive than LIGO, capable of detecting the mergers of black holes and neutron stars across the observable universe. LISA, the Laser Interferometer Space Antenna, would take the detectors into space. 3 spacecraft forming an equilateral triangle 5 million kilometers on a side, sensitive to gravitational wave frequencies inaccessible on the ground. These instruments will open portions of the gravitational wave spectrum that LIGO cannot hear. They will detect supermassive black hole mergers from billions of light years away, the slow inspiraling of compact objects around the central black holes of distant galaxies, and perhaps signals from the early universe itself, reverberations of processes that occurred in the first fractions of a second after the Big Bang, preserved in the fabric of space-time and waiting for instruments sensitive enough to read them. Every discovery changes what we understand the universe to contain. A planet orbiting 4 stars, metallic hydrogen raining helium inside a gas giant, water ice on the shadowed floors of craters in the airless cold, an asteroid landing that was never planned, a planet that died slowly over billions of years while keeping its water locked in ice, light bending around the curvature of space-time. and space-time itself rippling outward from collisions we can now hear. The inventory of what we do not know is longer than the inventory of what we do. That is not a failure of science. It is what science looks like when it is working.